Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the variation of fluid velocity with flow area. During fluid flow through many devices such as nozzles, diffusers, and turbine blade passages, flow quantities vary primarily in the flow direction only, and the flow can be approximated as one-dimensional isentropic flow with good accuracy. Therefore, it merits special consideration. Differentiating the continuity equation yields. For the incompressible fluid, such as liquids, we have. This means a fluid of liquid to be accelerated, such as syringes and fire hoses. A converging nozzle must be used. For the incompressible fluids, from the momentum equation, we have this expression. Differentiating the isentropic relation and rearranging, we can obtain. This implies variations of the specific volume and the velocity have the same trends. Combining these relations with the continuity equation, we have. This is equation 913. Differentiating the energy equation yields. Incorporating the second Gibbs relation yields. These relations describe the variations of velocity and pressure with flow area. At subsonic velocities, the pressure decreases in converging ducts and increases in diverging ducts. At supersonic velocities, the pressure decreases in diverging ducts and increases in converging ducts. Let's look at equation 913, which has been derived. This equation governs the shape of a nozzle or a diffuser in subsonic or supersonic isentropic flow. Noting that A and C are positive quantities, we conclude the following. For subsonic flow, since the Mach number is less than unity, we then have this relation. For supersonic flow, since the Mach number is greater than unity, we then have this relation. For sonic flow, since the Mach number is unity, we have this relation. Thus, the proper shape of a nozzle depends on the highest velocity desired relative to the sonic velocity. To accelerate a fluid, we must use a converging nozzle at subsonic velocities and a diverging nozzle at supersonic velocities. To accelerate a fluid to supersonic velocities, we must use a converging diverging nozzle. The velocities encountered in most familiar applications are well below the sonic velocity, and thus it is natural that we visualize a nozzle as a converging duct. However, the highest velocity we can achieve with a converging nozzle is the sonic velocity, which occurs at the exit of the nozzle. If we extend the converging nozzle by further decreasing the flow area in hopes of accelerating the fluid to supersonic velocities as shown in the figure. We are up for disappointment. Now, the sonic velocity will occur at the exit of the converging extension instead of the exit of the original nozzle, and the mass flow rate through the nozzle will decrease because of the reduced exit area. Based on equation 913, which is an expression of the conversion of mass and energy principles, we must add a diverging section to a converging nozzle to accelerate a fluid to supersonic velocities. The result is a converging diverging nozzle. The fluid first passes through a subsonic section, where the Mach number increases and the flow area of the nozzle decreases, and then reaches the value of unity at the nozzle throat. The fluid continues to accelerate as it passes through a supersonic section. Noting that the mass flow rate expression for steady flow, we say that the large decrease in density makes acceleration in the diverging section possible. An example of this type of flow is the flow of hot combustion gases through a nozzle in a gas turbine. The cross-section of a nozzle at the smallest flow area is called the throat. This figure shows the variations of normalized fluid properties and cross-sectional area along a duct as the pressure drops from 1,400 to 200 kilopascal. We note that the flow area decreases with decreasing pressure up to a critical pressure value, and then it begins to increase with further reduction in pressure. The velocity of the fluid keeps increasing after passing the throat, although the flow area increases rapidly in that region. This increase in velocity past the throat is due to the rapid decrease in the fluid density. The flow area of the duct considered in this example first decreases and then increases. Such ducts are called converging diverging nozzles. These nozzles are used to accelerate gases to supersonic speeds and should not be confused with Venturi nozzles, which are used strictly for incompressible flow. When the Mach number is equal to unity, the properties at the nozzle throat become the critical properties. The critical property is indicated by the subscript C. For example, PC is for the critical pressure, TC is for the critical temperature, CC is for the critical velocity. Okay, that's all for this task. Thank you very much and see you next time.